Obviously, we've not yet done how do we get this value, phi. Phi is the key to unlocking this process, and I've not yet explained how we get there. Well, there's an 8-step process. Now, steps 1 to 3, we've done before. That's chapter 5. Okay. Step 1, find the equation of motion. Step 2, find the mechanical impedance matrix, and that will give us the our natural frequencies. And then obviously you apply those natural frequencies back into the mechanical impedance matrix, and you get your mode shapes. Steps 1, 2, and 3 we've done already. Step 4 is new, and that involves determining a scalar quantity called the modal mass. Like I said, the maths, the derivation of this process is not going to be covered. But basically, what you do is you take your mode shape and your mass matrix, you transpose your mode shape so it becomes a row vector, times by your mass matrix, times by your mode shape again, which is a column vector. You end up with one value, a scalar, okay? And that scalar is known as the modal mass. That's mi here. And this equation is written for the ith mode shape, okay? And that m is the mass matrix from your equation of motion. So I'll give you mi. Now what you need to do is you need to rescale to make sure you get that identity matrix in front of the modal acceleration term. You've got to rescale our mode shapes, okay, to be, and that will use this equation. So we take our mode shape, we found mi in the previous step, you take the square root of it, and you divide your mode shape, each term in the mode shape, by the square root of your modal mass, and that gives you another vector, which is basically your mode shape, but rescaled. So originally, this mode shape will have 1 and then some other term, if you remember, okay? We set the top term to be 1, and everything else is relative to that first term. Well, basically, this is the same, it'll be the same ratio, it's just been rescaled by a certain constant. And then once you've got those, you basically line them up next to each other, and that gives you phi. And so if you've got a 2-degree of freedom system, each of these will be 2 terms. You'll have 2 of them, so you end up with a 2 by 2, which is your phi matrix. If you've got 3, you'll have 3 of these, each with 3 terms in, so you've got a 3 by 3. That will be your phi, and so on. Okay, and that gives us our modal matrix. Like I said, it's all to do with the modes. And by rescaling it, you get that identity matrix in front of the q double dot term, and you get your omega squared term in front of the q term. We've got to deal with that applied force using another equation. So we take the transpose of phi. Okay, so you swap the terms over around the diagonal, and you multiply that by your force vector to get a modal force vector. It'll come clear when we do the example, I'm sure. You then solve those equations, like I said, for an undamped case, they're always going to be in this form. Okay, so you can jump straight to them. And then you apply the substitution to get back to those expressions to get values for x, which is our displacement, which is what we're looking for.